Good afternoon, all.
Good afternoon, sir.
Good
Good
afternoon.
afternoon,
Good
sir.
afternoon.
Good afternoon, sir.
In the last class, we have proved the first property and second property, right? Am I audible?
Yes, sir, you are audible.
I have shown the proof of part A and part B, right?
Yes.
And third and fourth, these two are the application of part A and part B actually. If you simultaneously use part A and part B, then you will get this. Do I need to show it, or you can practice it from my note? Actually, that these are very simple. In the last class, I gave the idea. Do I need to show?
So it's
Okay. So, what is the first property? Uh, Proof of C. I'm doing. or 3 I can write. So we know that what x to the power nu j nu x d dx of this is equal to what? Tell me. X to the power nu j nu minus 1, right? This one d dx of x to the power nu j nu x is equal to x to the power nu j nu minus 1. Now if we differentiate it left side, then it will be what? X to the power nu j nu dash x plus nu x to the power nu minus 1 j nu x is equal to x to the power nu j nu minus 1 x. Fine.
Yes.
And what about the second property? Say it is equation number 1, and also we have d dx of x to the power minus nu j nu x. It is what? Minus x to the power minus nu j nu plus 1 x. Isn't it?
Yes, sir.
This one.
Yes.
Minus x to the power minus nu j nu plus 1 x. Now again for that you apply the differentiation. So x to the power minus nu j uh, nu dash x minus nu x to the power minus nu minus 1 j nu x j nu plus 1 x. Okay.
Yes.
Now see what we have. Tell me. Any doubt?
No, sir.
No, sir.
Okay. Now you have to see what we are going to prove. J nu. You see property number C. J nu minus 1 plus J nu plus 1. Okay. And another one, property number D, it is J nu minus 1 minus J nu plus 1. So what I will do, from the first, so I am dividing equation number 1, I am dividing equation number 1 by x to the power nu. Okay, so it will be what? J nu dash x plus nu x to the power minus 1 j nu x is equal to j nu minus 1 x. It is set 3 and 2, we are dividing equation number 2 by x to the power minus nu. Then it will be j nu dash x minus nu x to the power minus 1 j nu x is equal to minus j nu plus 1 x. Now you subtract these 3 and 4. Okay, so if you subtract these two, it will be what? J nu dash eliminated. It will be 2 nu x inverse means 2 nu by x j nu x is equal to right hand side j nu minus 1 plus j nu plus 1. So it is the third part, right? See,
Yes, sir.
addition of these two 2 nu by x j nu x. Fine. And that is the proof of third part. And if you add these two, 3 plus 4, if you add these two, then nu x to the power minus 1 j nu x cancel out. So it will be 2 j nu dash x, 2 j nu dash x is equal to j nu minus 1 minus j nu plus 1. Sorry, minus. So that is the proof of part 4, isn't it? It is the part 4 now. 2 j nu dash x. Any doubt? Tell me.
No, sir.
Actually, on addition and on subtraction, we are getting on addition of property number 1 and 2, and on addition of property number, sorry, subtraction of property number 1 and 2, we are getting 3 and 4. One time you have to subtract, other time you have to add. Okay. Now, see another important property. This one actually, here it is shown that if n is an integer, okay, if n is an integer, then j of minus nx is equal to minus 1 to the power n j nx. Means that is the relation among j of minus n and j of n. So when this relation holds, whenever n is any integer, rather positive integer. Do you get it? What is the claim? Do you understand or not?
Yes.
J of minus n is equal to minus 1 to the power n into jn. Now, can you tell me if n is a positive integer, then j of minus n and jn, are they linearly dependent or independent? you think about solution of ODE, two solutions y1 and y2. Okay, y1 and y2. So if y2 can be written as some constant into y1, then y1 and y2 are called
Dependent.
dependent. Or in the other term also you have learned ratio of these two is equal to constant. Right, same thing. If the ratio is constant, then dependent. If not a constant, then independent. Or in the other way, we can say if one is the constant multiple of another, then they are dependent. So what we can see that j of minus n, it is the constant multiple of jn. Na? Minus 1 to the power n, it is the it is a constant. So j of minus n, it is equals to some constant into jn. So what we can conclude? J of minus n and j of n, they are linearly dependent. Is not it?
Yes, sir.
Yes. Okay. So only when, do remember, not always they are dependent. Only when n is a positive integer. Then only resolve. Now how to prove it? Whenever n is a positive integer, j of minus nx is equal to minus 1 to the power n j nx. Okay, you can see it from the book. You just tell me. Um, Now, can you tell me what is the expression for JNX? JNX. Tell me. Anyone?
So m0 to infinity minus 1 to the power m x to the power 2m plus n.
This. Then
2 to the power 2m plus n divided by m factorial n plus m factorial.
this. Correct. Now, according to it, what will be J of minus n? So in place of n, if we put minus n, we are done, right? We will get the series. In place of n, if we put minus n, so we can write this. Do you get it? Just I have replaced n by minus n. Then it will be the expression for j of minus nx.
Yes, sir.
Now what will be the limit? 0 to infinity or something else? Look, if you put m is equal to 0, have there any contradictory part? Means by mistake, if you take m 0 to infinity. Now for m is equal to 0, is every part is defined? It is what? Minus n factorial. If you put m0 minus n factorial, it is negative, right?
Yes, sir.
And negative का factorial होता है?
No, sir.
No. So from where it will be positive, that m minus n, 0 or positive?
N.
N means m, if m is equal to n and more than that, then this factorial is defined. M is, if m is equal to n, then it is what? 0 factorial and it is defined. And if m is equal to n plus 1, then it is 1 factorial. And rest of the parts are defined if you take m greater than n. So actually here for the undefined terms, we are not taking, we are taking from where it is defined. So from m is equal to n, it is defined. So I am taking m is equal to n to infinity. Do you get it? What is the reason behind it? Why I am taking m is equal to n to infinity?
Yes, sir.
Others?
Yes, sir.
Okay, now to express it, to express that j of minus n in terms of jn, limit should be 0 to infinity, right? But here limit is from n to infinity. So how to convert it to 0 to infinity?
Sir,
Huh?
sir, can you explain this one? Why m equal to n? Sir, it will zero, na totally the denominator will be zero.
Look, if you put, means if you want to unchange it, means remains, if it remains same, means m 0 to infinity, if you think in that way, put m is equal to 0, then what will be the term? Is it a valid term for m is equal to 0?
No, sir.
Here,
No,
this
sir.
term, is it valid for m is equal to 0?
No, sir.
No. So because that that term will be minus n factorial, right? And which is undefined. So similarly, 1. If you take m is equal to 1, then it is also 1 minus n. And if n is greater than 1, then it is also negative. So, but if m, we start it from n, it never be negative, right? 0 and positive are terms we will get. Means we will get defined terms from m is equal to n. Valid terms. Are you getting?
Yes, sir. Yes.
Okay, so m start from n to infinity. Now, to start the limit from 0 to infinity, we take m minus n is equal to s. Okay, so if we take m minus n is equal to s, then limit for s will be, put m is equal to n, then s will be 0. And in the rest part also, you put m is equal to s plus n. M is equal to what I told, s plus n. So 2s plus 2n minus n, 2s plus n divided by 2 to the power 2s plus n, s plus m is equal to what? S plus n factorial and m minus 1 is factorial. Now what is coming? Look, now minus 1 to the power s plus n. I can write it minus 1 to the power s into minus 1 to the power n. Okay. And then you bring that minus 1 to the power n outside the summation. Then the rest of the summation, it is what? Is not it jnx?
Yes.
Yes.
Yes, sir.
If you think that no, I could not understand this part. Why it is jnx? So s is the dummy variable. You can substitute that s by m again. Okay, so you substitute s is equal to m, then it is jnx. You see. Look, the most interesting part is the first part here, the lower limit. That is the main part in this derivation, isn't it? If you start with 0 to infinity, then it becomes wrong. Summation should start from n to infinity. And then m minus 1 is equal to s, and you will get the result. Is everything clear?
Yes, sir.
Yes, sir.
Okay.
So do you have to remember this derivation?
Yes, yes. You have to remember. I don't know why it is not in my. It is not written in my note. Mostly I have written as I can remember, but I don't know why I can see the proof. Even I used download this Jamboard, okay, and I think in the book also it is written clearly. The proof is given. Yes, just this line: j of minus n to infinity, and then substituting a minus n is equal to s, we are getting the result. Fine. So the proof is there in your book. Fine. Now the last theory part I'm going to conclude. We are going to solve more problems from here, but last theory part is that what we have seen, if new means j new in that j new x, okay, if new is an integer, new is a positive integer, then j new and j minus new, they are dependent, right? That we have proved right now. It's just we have proved. If new is an integer, positive integer, j nu and j of minus nu are dependent, and they are related by this relation. And in other cases they are independent, means except integer case they are independent. So whenever we solve the Bessel's equation, we got the value of r, it is minus plus nu, right? These are the roots of the initial equation. So one solution that is represented as j nu x, and according to the Frobenius method, other solution may be j minus nu x, because roots are plus minus nu. So for plus nu we are getting j nu x. Accordingly for minus nu we can think the solution is j of minus nu. Is not it? Like y1 and y2. y1 is our j nu x and y2 our j of minus nu x. Now the question is, are they form general solution? Means can we write general solution by j nu and j minus nu? So to write the general solution, y1 and y2 should be linearly independent, right? Basis of solution should be basis of solution. Now here what we can see, that j nu and j minus nu are dependent when nu integer. Means whenever nu is an integer, in that case I cannot write c1 j nu plus c2 j minus nu is a general solution, because j nu and j minus nu are dependent, and apart from it we can write the general solution. Means if nu is not an integer, in that case c1 j nu plus c2 j minus nu, that is a general solution. Do you get it? I am talking about the solution of Bessel's equation. So j of nu x, it is one solution, na? J of nu x. For r is equal to nu, we got j nu x. Similarly, other solution should be j of minus nu x. But you have to verify when they are dependent and when they are independent. If they are independent, they form basis of solution. Therefore, we can write the general solution. And if they are what? Dependent, then we cannot write the general solution. There is a conclusion about the solution. Whatever I told, everything explained here. In देखो यहाँ पे लिखा होगा. Since Bessel's equation involved nu square, the function j nu and j minus nu are solutions of the equation. Equation means Bessel's equation for the same nu. If nu is not an integer, they are linearly independent. Isn't it? अगर integer हो जाएगा, then they are dependent. We have seen. But if nu is not an integer, they are linearly independent. And thus we can thus if nu is not an integer, a general solution for Bessel's equation is this: yx is equal to, means y is equal to c1 y1 plus c2 y2. So c1 j nu plus c2 minus j nu. When? Again I am repeating. When we can write this general solution? If nu is not an integer. Okay.
Yes, sir.
Now I am showing you some exercise problems. See, you just compare this problem number 2. Uh, you just compare with the Bessel's form. What is new? What is new? 4 by 49. Means, sorry, new square is 4 by 49. Do you remember the form? Form of Bessel equation? X square y double dash plus xy dash plus x square minus new square y is equal to 0. So what is new square? 4 by 49. New will be
2 by 7.
2 by 7. Don't consider minus 2 by 7. New will be plus minus 7, but sorry, plus minus 2 by 7. Since new is a positive integer, sorry, positive real number, na? In the definition, in the construction of Bessel's equation, it is stated that new is positive. So you have to consider new 2 by 7, not minus 2 by 7. So new 2 by 7. Therefore, it is not an integer, right? Now I can conclude that the solution, the form of the general solution for this problem number 2 will be in that form. Y is equal to C1 J 2 by 7x plus C2 J minus 2 by 7x. Okay, so we will get this type of general solution because new is not an integer. बट मान लो कि ऐसे इक्वेशन दिया है एक्स स्क्वायर वाई डबल डैश प्लस एक्स वाई डैश प्लस एक्स स्क्वायर माइनस 4y is equal to 0. Then what is the value of new? 2. Right?
Yes, sir.
New 2. Now can you tell me that whether we can write the general solution or not? Can I write general solution in that way? C1 J2x plus C2 J minus 2x. Will it be a general solution?
No, sir.
No. Because J2 and J minus 2, they are dependent. Okay. So this cannot be general solution. Actually, there have some solution to get rid of this type of problem. If mu is integer, then how to write the general solution? In that case, we will consider second kind of Bessel function. Okay. I told na J nu it is called first kind. Bessel function of first kind, is not it? So whenever new integer, in that case to write the general solution, we need second kind of Bessel function, which is denoted as y new, and it is not in your syllabus. Second kind of Bessel function, it is not in your syllabus. Okay. It is in actually 5.5 Bessel function of second kind. It is not in your syllabus. Now we will solve some integration and some more results on the Bessel function. Like at least these two, there will be proof of these two, so that half j half x is equal to this and j of minus half x is equal to this. Okay, uh, proof of this statement may come. J half is equal to root under square root of 2 by pi x sin x, and j minus half square root of 2 by pi x cos x. So in the next class I will show you these two proof, and there are some other problems related to integration of Bessel function. Okay, integration of Bessel function and differentiation of Bessel function also. Like that problem number 23, so that integration of x square j naught x dx is equal to x square j1 plus x j naught minus integration j naught. Also, this type of problem may come, so that j1 dash x is equal to j naught minus j1 by x. So to prove this, we basically use those four properties which earlier we have proved. Okay, property 1, 2, 3, 4. Those four properties we are going to use. So from 2 to 10, there are some problems where we have to convert the given equation to Bessel's form. Okay, reducible to Bessel's ODE. And then you have to state what type of solution it has. So I will mark those type of problems, and then this problem number 19 and 21, 22, 23, 24, 25. Look, 21, 22, 23, 24, 25, these are related to integration of what? Bessel's function. These are formula actually, 21, 22, these are formula, and these are coming from those properties actually. Property number 1, 2, 3. I will show you in the next class. So, it will take 2 more class to finish the chapter 5. Okay, it is the last section, 5.4. So only 2 classes. And that's all for today. Fine, I will not do anything more.
Okay, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Your attendance?
Wait,
Attendance?
don't leave. I'm going to take attendance.